When designing a database, one of the most important principles is organizing data logically. Instead of placing all information in a single table, we divide it into groups, based on related data. Each group is represented by a table, making the database more structured, efficient, and easier to manage. Let us look at a simple example, a business that sells products online. This business has customers who place orders. If we stored everything, that is, customer details, order information, and product detail, all in one table, it would become large, inefficient, and difficult to update. Instead, we break the data into logical groups, with each group represented by its own table. A customer's table, for instance, stores customer information, like customer ID, name, email, address. An orders table stores order details, such as order ID, customer, which links to the customer's table, order date, total price. By separating customers and orders, we achieve clarity and flexibility. If a customer places multiple orders, we simply add more rows to the orders table without duplicating their details in every record. Why does this matter? It minimizes redundancy, we avoid storing the same information repeatedly, which reduces data duplication and saves storage space. It ensures data integrity. If a customer updates their email or address, we only need to change it in one place, rather than searching through a massive table. And it improves performance. Smaller, well-structured tables make queries faster and more efficient. Each table in your database should have a clear role and purpose. By grouping related data logically, you create a database that is easy to manage, scalable, and efficient. In relational databases, tables are not isolated, they often need to be connected to represent real-world relationships. One common example is linking clients and orders. Let us break this down using the following two tables. Create table. Clients. Client_ID. Character 15. Create table. Orders. Client. Character 15. Here, both tables have a client-related field. The clients table stores information about clients, and it has a column called client_ID. This client_ID is a unique number or code for each client, so no two clients have the same one. The orders table keeps track of orders, and it has a column called client. This client column shows which client made the order, linking back to the client_ID from the clients table. Notice that both fields use the same data type, character 15. This is crucial for maintaining consistency and ensuring the database can correctly associate records between these tables. If these fields use different data types, such as client_ID being an integer in one table but a character in the other table, it could cause compatibility issues, making relationships difficult to manage. By keeping both fields as character 15, we ensure that data can be accurately linked. With this setup, every order in the orders table is associated with a client from the clients table. The client value in the orders table corresponds to the client_ID in the clients table. One small note, the client field in the orders table corresponds to the client_ID field in the clients table. While you could name the field in orders something unrelated, like house, it would still function. However, that would make it harder to understand what the field represents or what kind of data it holds. To keep things clear, I recommend using similar names for related fields or referencing the source table, like client or client_ID here. Let's continue. If the clients table has an entry client_ID equals C123, which represents John Doe, then, in the orders table, client equals C123 in an order means that John Doe placed that order. This link between tables allows us to efficiently retrieve data. For example, we can find all orders placed by a specific client using a join query, rather than storing redundant customer details inside the orders table. Always ensure that linked fields in different tables use the same data type for smooth relationships. The client field in the orders table acts as a reference to the client_ID in the clients table. By structuring data in separate tables, we avoid redundancy and improve database performance. This approach is fundamental to relational databases, making queries more efficient and data more manageable. In a relational database, consistency is key, especially when working with related tables. Let us look at the client column, which appears in the orders table, and references the client_ID column in the clients table. Since this column represents the same piece of information in both tables, it is important to maintain consistency in its data type throughout the database. For example, if client_ID in the clients table is defined as client_ID, character 15, then the corresponding client column in the orders table should also be client, character 15. This ensures that data can be accurately linked between the two tables. Why the repetition? Next slide has the answer. What happens if the data types do not match? If these fields had different data types, you would run into problems when joining tables or filtering data. For instance, if client_ID were stored as an integer in one table, but as character in another table, the database would not recognize them as the same type. In that case, you would need to use a conversion function like cast, or convert, to make the data compatible, which adds unnecessary complexity, and can slow down queries. Imagine, client_ID is 123 in the clients table, an integer, but 123ABC in the orders table, a character. A simple join between these two tables could fail, because 123 and 123ABC are not equal, even if they look similar. You have to cast one to match the other, which could confuse things if you are not careful. To avoid these headaches, it is a good idea to double-check that related fields, like client_ID and client, use the same data type when designing your tables. Consistency here saves time later. Using cast or convert forces the database to process every row on the fly, which can really bog down performance if you are dealing with millions of records. It is like asking the database to translate a book word by word, instead of just reading it. Cast and convert are expensive, they burn extra CPU and memory. Personally, I think it is better to avoid them altogether. The real fix is ensuring related fields use the same data type from the start. Designing your tables with consistency in mind saves time, keeps performance sharp, and skips the hassle of conversions. Consider the following example from the slide. 1. First we create a table. 2. We insert a value, 123. 3. We convert 123ABC to 123 with cast. 4. The result is 123. As you see, this is a lot of typing every time you need to compare across tables. An alternative is to create views or functions, but it is always better to avoid cast or convert at all. Primary and foreign keys. While primary and foreign keys are not strictly required, they are strongly recommended for a well-structured database. A primary key ensures that each row in a table is uniquely identified. In our case, client_ID in the clients table would be our primary key. A foreign key, like client in the orders table, would reference client_ID, ensuring that every order is linked to a valid client. By defining these keys, you get several advantages. Data integrity: the database prevents orphaned records, meaning you cannot have an order linked to a non-existent client. Faster queries: joins and lookups run more efficiently with properly defined foreign keys. Clearer relationships: it is easier to see how tables connect. There is no official naming convention for primary and foreign keys, so here is my approach. I add _ID to a column that will be referenced elsewhere, like client_ID, making it a potential primary key. Columns referring to it, like client in another table, are potential foreign keys. You will need to explicitly define these keys and constraints to activate their power, more on that in a sec. Now that we have cleaned up our client_ID and linked it to client, let us talk again about why matching data types and using keys can save you headaches down the road. Always use the same data type for related fields across tables to ensure smooth operations. Mismatched types cause conversion issues and drag down performance. Use primary and foreign keys, they enforce data integrity and speed up queries. A well-structured database makes data management easier, more reliable, and faster. Let us step back to why primary keys matter for uniquely identifying data. Uniqueness is crucial. When you set a primary key like client_ID, each value must be unique. No two clients can share the same client_ID. The database enforces this, blocking duplicates. It cannot be null, so every row has a valid identifier. Think about it, if two clients have the same name, how do you know who placed an order? If order numbers repeat, how do you track the write history? Uniqueness ensures accuracy, avoids confusion, and makes searching and linking records a breeze. Referential integrity is key in database design. It ensures relationships between tables stay valid. Some developers skip database constraints and handle this in application code instead. That is a risky move, complex, error-prone, and a recipe for trouble. Let us break it down. Referential integrity means a record in one table must match a valid record in another. Take our clients and orders tables we created earlier in this video. We simply created the two tables, we did not assign any primary key of foreign key, we also did not set any constraints. Since we did not set any constraints here, nothing stops an order from linking to a client that does not exist in the clients table. Some apps try to enforce this manually in code, checking. Does the client exist before adding an order? If a client is deleted, are all their orders deleted too? What if two processes write data at once? This approach has big downsides. Complexity, extra queries to validate every insert, update, or delete. Slowness, application level checks lag behind database constraints. Fragility, miss one validation, and data consistency crumbles. Orphaned records, I have seen applications fail at this, orders tied to ghost clients, deleted codes haunting reports. Even solid applications can slip. Add a new feature, skip one check, and inconsistencies creep in over time. A better approach is to let the database itself enforce referential integrity using foreign keys. I added the primary key to the clients table. Now we need to add the constraint to the orders table. So, let us modify our orders table. Create table. Orders. Order_ID. Integer. Primary key. Client. Character 15. Constraint. FK_client. Foreign key. Client. References. Clients. Client_ID. On delete cascade. In constraint FK_client, foreign key, client. The part FK_client is the name of the constraint. Now, the database prevents invalid data, you cannot insert an order for a non-existent client. Ensures consistency, if a client is deleted, related orders are automatically removed, because of on-delete cascade. Improves performance, these checks happen at the database level, reducing the number of queries needed. Application-level referential integrity is fragile, it is easy to miss a validation, leading to corrupted data. Database constraints enforce consistency automatically, foreign keys prevent invalid relationships. Using database rules simplifies development, you do not need extra queries or manual checks. By relying on database constraints instead of complex application logic, you reduce errors, improve data consistency, and make your application more reliable. When working with databases, data integrity issues do not always show up where you expect them to. In the core, well-tested parts of an application, where users interact with the data regularly, problems like orphaned records are less likely to occur. If something breaks in a frequently used feature, users will notice quickly, and developers will be alerted. But what about the lesser used parts of the application? These areas, often overlooked during testing or updates, are where data integrity issues quietly take hold. Maybe there is an old module that still processes customer data, but no one checks it often. Perhaps a background process imports external data, but the validation rules are not strict. Or an administrator-only feature allows manual record deletion, but it does not check related tables. When these sections of the system are not frequently tested, referential integrity checks can be forgotten, and orphaned records start accumulating unnoticed. One reason why orphaned records persist is the lack of immediate failure. If an order references a missing client, but the application does not crash, the issue may remain hidden. There is no visible error message. Reports still generate results, but sometimes just with missing details. The problem is only discovered when someone digs deeper into the data. Over time, these inconsistencies snowball, making it harder to clean up later. To prevent orphaned records, it is essential to regularly audit lesser used areas of the application. Implement database-level constraints, not just application logic. Use automated integrity checks to flag missing references. By ensuring data integrity across the entire system, not just the most visible parts, you protect your database from long-term inconsistencies and unexpected failures. Orphaned records might seem like a minor issue at first, but over time, they can lead to serious problems that affect both your data and your application. When records lose their connection to related data, they disrupt the accuracy and reliability of your database. This has several consequences. 1. If a reporting tool pulls data from multiple tables, and some records have missing references, reports may produce incomplete or misleading results. A sales report might show fewer, or more, completed orders than actually exist. A customer activity log might miss certain interactions, because they reference a non-existent user. Financial summaries could have gaps, leading to incorrect decision-making at higher levels. When businesses rely on data-driven insights, inconsistent data can lead to costly mistakes. 2. Developers often assume the database is clean and well-structured. If orphaned records exist, new features might break because they depend on data that should be there, but is not. A feature that links customer history to orders could fail, if those orders reference missing customer records. A migration script might crash when encountering relationships that should not exist. An automated process that updates records could behave unpredictably, corrupting more data. These issues slow down development and require extra work to fix. 3. When data is inconsistent, the application might behave in ways nobody expects. Users might see empty drop-down menus where data should be pre-filled. System calculations could return incorrect or partial results. Deleting a record might leave behind unusable, floating references that cause silent failures. Debugging these problems is difficult because the root cause is not always obvious. It might take hours to realize that the issue stems from orphaned records rather than a code bug. Preventing long-term issues. Enforce referential integrity at the database level with foreign key constraints. Regularly audit and clean up orphaned records. Use test cases that specifically check for missing relationships. By taking these precautions, you keep your database reliable, scalable, and easier to maintain, preventing costly issues before they arise. There is another solution you can try when you have time. At my former job, I worked with a database that lacked primary and foreign key constraints, which made it prone to orphaned records, rows in a child table that reference non-existent entries in a parent table. To address this, I periodically attempted to establish primary and foreign key constraints on various tables in a test environment. When I encountered errors indicating that the constraints could not be applied due to orphaned records, I used these failures as a guide to identify and remove the problematic data. By querying the child table for rows where the foreign key value did not match any primary key in the parent table, I could locate these orphans and delete them, gradually cleaning the database and enabling proper relational integrity. This brings us to the end of this video on creating tables and exploring the theory. In the next video, we will dive into the insert into command, which lets you add new rows of data to your tables. I look forward to seeing you there.